Hello everybody. Today we discuss propositional logic or Boolean logic or zeroth order logic on the general topic of the series of lectures on logical deduction in artificial intelligence. Logic and deduction have a very long and ancient history. Other than today's modern logic and theory of logic and its relationship with many other things like number theory, computation, circuits, and several other things, logic has had a history which developed independently as well as with interactions of various civilizations. In the Indic school of thought, geometry and various calculations in any case required logic. So logic was embedded in geometry, in calculations, in mathematical principles. However, slowly, logic became a discipline of its own, and in the six systems of philosophy of Indian philosophy, which consists of the Shad Darshan or the six systems, Nyaya, particularly the Nyaya school, was the school of logic. There was also logic in Vaisesika, and there was logic in various others, including Vedanta, which we shall see later. Logic was processed by a theory of argumentation and debate. There are very well-known famous debates in the history which talks about people sharing their arguments with somebody else and then defeating somebody in a series of arguments. And there are several such case studies which we can find. Among the methodologies used, the language of Sanskrit was a very powerful tool, especially with its binary level and multimodal level of arguments. The language of Sanskrit, being very precise in its grammar, in its syntax and its semantics, provided a very natural mechanism for doing argumentation and explaining things in logic. That is why we see that the language of Sanskrit was not only used for literature, it was used for mathematics, it was used for debates, it was used for propounding theories, and it became a generalized language which embedded in it the whole of logical arguments. The logical argumentation theory evolved into what is called the four-armed logical principle or Chatushtoki. Parallel to this Indic thought, the Buddhist thought and the Jain philosophies, which moved in parallel, almost in parallel from the 6th century BC onwards, had their own principles which overlapped to a great extent and formed the overall system of the Indic logic. Finally, the formal systems came up, and one of the most profound aspects of Indian logic is not only to look at material aspects, but to look at deeper philosophical aspects of life, its meaning, and everything else which was discussed in the profoundest of logic in Vedanta, and there is this whole set of Vedantic philosophy. China, in parallel, through the great philosophers Confucius, Mozi, and Master Mo, developed their own philosophical schools, and they started to develop basic formal systems. Finally, the Buddhist philosophical systems came into China and had a profound influence on the Chinese philosophies. Even from the Buddhist philosophies of China also affected the Tantric philosophies of India. The other great school of philosophy, which is very profound, which had a deep impact on modern philosophy, was the Greek philosophy. The Greek philosophy originated from geometry and mathematics through Thales and Pythagoras and various other people. And it is there they started producing propositions in geometry, theorems, and logical arguments to prove these theorems. Then from there, slowly, the concept of logic as an independent school, as an independent subject, came through Heraclitus and Parmenides. Finally, Logic beyond geometry was enunciated by the great Plato, and the most significant influence, the profound influence of Aristotle, who systematized logic as a discipline of its own, providing it with syntax, with semantics in his famous books, has had a profound impact on Europe and the subsequent logic that we do today. There were other schools like the Stoics and others. The Middle East, both ancient Egypt and Babylon, through their constructions had a deep geometric and mathematical and land calculation logic. However, the Arabs, with a series of great logicians, developed over the Aristotelian logic system into what was known as the Avicennian logic, and they were the first to look at concepts like inductive logic. At the same time, in medieval Europe, post-Aristotle logics developed, and a precursor to the first order logic that we shall do in subsequent lectures also developed. Today, logic is a very, very deep discipline. Today we will discuss propositional logic, which is the first phase. Then there is predicate or first order logic, there is higher order logic, and logic has got an intricate relationship with numbers, with computation, with circuits, with psychology, with philosophy, and with various kinds of networks, including brain computation, brain networks, neural networks, and things like that. So, how decision making occurs and how logic works is one of the most interesting topics in artificial intelligence. And today we shall do the first step of propositional logic. Propositional logic can also be called Boolean logic, from the name of George Boole, who developed this binary logic into a systematic circuit theory, and which also has got very other profound implications. Though all the other, whether it's Indic or Greek or Chinese or Middle East or medieval Europe, all of them had it in this form. But however, we salute George Boole, and today this propositional logic or zeroth order logic is named after Boole and is also called Boolean logic. We shall discuss Boolean logic in this lecture. Let us look at the first few examples. The first example says, if I am the president, then I am well known. It also says that I am the president, and therefore it tries to conclude that so I am well known. All of us know that this statement is correct, because if I am the president, then I am well known, if that is a rule, and I am the president is known, therefore I am well known is obvious. So this we know is right. Let us look at the second one. The second one is very similar to the first one and says that if I am the president, then I am well known. So this first part is the same as the second part. But it says I am not the president. And it tries to conclude that I am not well known. And you will notice that this conclusion is actually not correct. This conclusion is not correct because while the first statement says that if I am the president, then I am well known, it does not say that if I am not the president, I am not well known. So this is where logic needs to be very precise. Since it does not say that if I am not the president, I am not well known, therefore, when I am not the president, it is not necessary that I am well known. But how shall we establish this as an infallible argument? We know through intuition that what we are saying is okay. Let us look at the third one. It says Rajat is the president, then Rajat is well known. It also says Rajat is the president, so it concludes Rajat is well known. Obviously, this is correct. And this has a stark similarity with the first one. So we must be able to show that the structure of the first one and the structure of the second one are identical. Then there are two more examples. If Asha is elected the vice president, then Rajat is chosen as general secretary and Bharati is chosen as treasurer. Rajat is not chosen as general secretary, therefore Asha is not elected the vice president. It is similar to all these above. The fifth one is if Asha is elected vice president, then Rajat is chosen as general secretary and Bharati is chosen as treasurer. Rajat is chosen as general secretary, therefore Asha is elected vice president. Now which of them is correct? Which of them is wrong? How do we analyze? All of them look similar, but how do we bring about this in a formal system? That is what we do in what is called propositional logic or Boolean logic. So what do we do in Boolean logic? We take these English language sentences. First, we choose a set of Boolean variables A, B, C, D, which can take values true or false. So propositional logic only consists of Boolean variables which can take values true and false. Then we form Boolean formulae. How do we form? We shall come to. And these Boolean formulae are formed based on the Boolean logic operators not, and, or, and implies. There could be other operators. The meaning of these are given by the truth tables which all of us know. Then we take the sentences which are given to us like we saw in the previous 5 examples, and we convert them into Boolean formulae using these Boolean variables. After that, we develop a deduction process and find out a combined formula which expresses the complete argument. And then we try to determine whether this formula is always true, sometimes true, never true, etc., etc. This is the process, and we shall now go through this process through a series of examples. So we take our first example. If I am the president, then I am well known. I am the president, so I am well known. So we now do our first step, choice of variables. We choose A and B because there are only 2 unique kinds of arguments here. The first we choose A, which we encode as I am the president. B encodes I am well known. Now let us look at the first sentence, F1, which says if I am the president, then I am well known. So we encode that as mentioned here as A implies B. A implies B is the same equivalent to not A or B. This is the truth table. It says if A is false, then A implies B is true. Otherwise, if A is true and B is true, then A implies B is true. A implies B is false only when A is true and B is false. So there is a truth of A implies B when A is true and B is true. There is also a truth of A implies B when A is false, which is it is true vacuously. The second sentence says I am the president. So we encode it as I am the president. And my conclusion says so I am well known. So we encode it as B, which is I am well known. So my formula which I need to prove is this. If F1 is true and F2 is true, then G is true. So my final formula, which encodes, as we said in this step, the combined formula, which encodes everything, is F1 and F2 implies G, which is the same as this. Because this part is F1, this part is F2, and this part is G. So as we said, the steps are choose Boolean variables, codify the sentences into Boolean formulae, develop a combined formula, and then we determine its truth. So now till now we have now codified the sentences and developed a combined formula. We now come to the details of the fourth part, last part, which is determining the truth or validity. So we look at the same example, and in this example, what we first do, we use a method called the truth table method. The truth table method lists out the truth of the formula for all possible combinations. Since we have two variables a and b, there are four possible combinations. And these four possible combinations consists of the values of a and b being true or false. So a and b being both true, one of them being true and one of them being false, and both false. Now when a and b are having these four rows in the truth table, a implies b attains this truth, because a implies b is true if a and b are both true and if a is false. The second part is a implies b and a, which is this part of our formula. So when a implies b and a is true and a implies b is true, so this is true. A is true, a implies b is false, so this is false. And since a is false in both of them, this is false. So now we have this being true, and in these three cases, this being false. Now we come to our combined formula. Our combined formula says the left hand side implies the right hand side. Now, wherever the left hand side is false, by implication rule, this is anyway true. On the other hand, when this is true and this b is also true, so this is true. So now we see that for all possible combinations of a and b, the final combined formula that we had is true under all cases. Therefore, this formula is a tautology. Therefore, we can now say that this sentence is true under all circumstances. So these circumstances, each of these rows, which is a circumstance, is called an interpretation. Since this formula is true under all interpretations, we now have a precise argument to explain to anybody why this logical deduction is correct. This is the method of using propositional logic to perform deduction. Let us look at the second example. The second example says had the first sentence as the same, but the second was I am not the president. And the question was I am not well known. So we do the same encoding. A is I am the president, B is I am well known. The first statement F1 is A implies B. The second is I am not the president, so it is not A. And the goal is I am not well known, so it is not B. And again we develop this truth table. And for this truth table, up to this part is same. Here, because this is not A, therefore it changes. And because this is not B, therefore we have a case where the formula is false. So it says that there is a situation when A is false and B is true. In that situation, if I am the president, then I am well known is true. If I am the president, then I am well known is true. But, and even the left hand side is true. That means up to here is true. But since A is false and B is true, therefore not B is false. Therefore this formula is false under this interpretation. And therefore we cannot always conclude that this overall argument is correct. As we just said a little while earlier, because if I am the president, then I am well known, does not imply if I am not the president, I am not well known. This precise argument clearly comes up here, and we can show that these sentences, this conclusion which had said I am not well known, is not derivable from the previous case. So now we have two examples which look very similar, and the precise manner by which we will be able to prove whether it is true or whether the deduction is correct or not is through the truth table. Let us look at the third example of Rajat is the president, then Rajat is well known. Rajat is the president, so Rajat is well known. So we code A as Rajat is the president, B as Rajat is well known. And if we code them, then we see F1 is A implies B, F2 is A, and G is B. And if we code this formula, we notice that both formulae are identical. And it gives us an idea that whatever we had the hunch of, that both are actually the same logic, just I was changed to Rajat, it does not make a difference in the sequence of arguments, is brought up very clearly to show that these two formulae are also identical under the same naming of variables. Now let us do the other two examples. This example says if Asha is elected VP and then Rajat is chosen as GSEC and Bharati is chosen as treasurer. The second sentence says Rajat is not chosen as GSEC, therefore Asha is not elected VP. So what will be our variables? Our variables will be A, Asha is elected VP, B, Rajat is chosen GSEC, C, Bharati is chosen treasurer. And then we start coding our sentences. Our first sentence F1 is if Asha is elected VP, then Rajat is chosen as GSEC and Bharati is chosen as treasurer. So A implies B and C. F2. Rajat is not chosen as GSEC, so not B. And our goal is Asha is not elected VP, which is not A. So if we want to put it clearly, this will be in this brackets. And in order to prove that this argument is correct, we again have to do the same thing. We have to prove F1 and F2 implies G. This formula is a tautology or not. And since there are three variables, the truth table here, the truth table will have 8 rows. So I leave it to you as an exercise to prove whether this is true or false. And if it is not false, if it is not true in all the rows, all the 8 rows, then the row in which it is false will provide you with a counter example. Let us go to the second one, which is very similar. In the second one, if Asha is elected VP, then Rajat is chosen as GSEC and Bharati is chosen as treasurer. This part is the same. Rajat is chosen as GSEC. This is different. Therefore, Asha is elected VP, which is different. So our variables are all the same. So our F1 here in this case is the same as the previous one. A implies B and C. Our F2 in this case is Rajat is chosen as GSEC, which is B, and goal is Asha is elected VP, which is A. So here again we will want to prove in this particular case whether F1 and F2 implies G is true under all interpretations. Is being a tautology means is true under all interpretations or not. So this is how we start coding these examples. Just for your interest, this part, A implies B and C, is the same as A implies B and A implies C. Because if A is true, both B and C are true. So therefore, this is the same as this. This is just for your, once you know the rules of Boolean logic, you can modify Boolean logic. You need not use truth table. You can also use the axioms of Boolean logic to try and prove this, and we shall discuss this a little later. We do two more examples, very similar examples. If Asha is elected VP, then Rajat is chosen as GSEC or Bharati is chosen as treasurer. Rajat is not chosen as GSEC, therefore Asha is elected VP. Therefore, this part again gets changed into a longer goal. So again we have our same variables. A is for Asha, is elected VP. B is for Rajat, is chosen GSEC, and C is for Bharati, is chosen treasurer. And what is my F1? F1 here is if Asha is elected VP, then Rajat is chosen as GSEC or Bharati is chosen. So this is this or C. Whereas in the previous case, it was and. In this case, it is or. F2. Rajat is not chosen as GSEC, and my goal is now a longer sentence. My goal says, therefore, if Asha is elected VP, then Bharati is chosen treasurer. So it is A implies C. This is my goal. Again, I have to prove the same thing. F1 and F2 together implies G. Whether this is true under all interpretations or not. I just want to put in a slight carefulness here. Whereas in the AND case, which we saw, A implies B and C was A implies B and A, but we cannot decompose this as A implies B or C is A implies B or A implies C. You can find out. Now we come to this case where we now say that if Asha is elected VP, then either Rajat is chosen GSEC or Bharati is chosen treasurer, but not both. Rajat is not chosen GSEC, therefore if Asha is elected as VP, then Bharati is. So the rest of them are same. So here only my F1 is a little different from the F1 in the previous example. So here it says it is either or but not both, which means it's an exclusive or. So it says if Asha is elected VP, then there are two cases that can happen. Either Rajat can be chosen as GSEC or Bharati treasurer, but not both. So either it will be B and not C, or not B, not B and C. So this is the formula. This is the B exclusive or C. F2 and is the same as before. G is the same as before. And the method remains the same. It is just the coding which differs. Again, we have to prove the same thing, whether or not this is true under all interpretations. So as I said, propositional logic method consists of determining a set of Boolean formulae, based on these Boolean formulae, codifying the sentences into formulae, finding out the combined formula of all the sentences, and then using some method like the truth table method or any other method which we shall discuss to determine whether this formula is true under all interpretations, all cases, or whether there is a case for which this formula is not true. So, the methods for deduction in propositional logic is to determine the interpretations of a formula. An interpretation is the truth of a formula under assignment of Boolean variables to true or false. So given a set of Boolean variables, once we know whether each of them is true or false, then we can determine the value of the formula. And once we know the value of the formula, which is true or false, that will give us an interpretation. A formula is said to be valid if it is true under all interpretations. This is the same as tautology. A formula is said to be non-valid if there is an interpretation for which it is false. Similarly, a formula is said to be satisfiable if there is an interpretation for which it is true. And a formula is said to be unsatisfiable if it is false under all interpretations. So based on these, now we also know that given a Boolean formula, because it is finite, it is decidable. That means we can know, but it is an NP-complete problem, which means that till now we do not have a fast polynomial time algorithm for it. We have seen how to do it by truth table method. There are other ways to do it. So suppose a formula has got three variables A, B, and C. The tree method will start with the formula and will choose one of the variables and assign it to be true or false and see what is the new formula. By this, in many cases, we could determine the truth under partial assignment. That is why it can become a faster method. There are other data structures, of which one famous data structure is a binary decision diagram, which can encode such Boolean formulae, and binary decision diagrams under certain cases of the same ordering are canonical. That means two binary formulae of the same Boolean expression under the same ordering will have identical binary decision diagrams. And then determining the truth, determining identicality, determining canonicity, all that is simply done by binary decision diagrams. There are also other types of methods to find out, which we shall see later, using the satisfiability methods and the unsatisfiability methods. We can also do it symbolically using axioms. All of us remember the axioms of Boolean logic, and using the axioms of Boolean logic, we could show how we can do it without writing a truth table, but by simplification of formulae, which we have already done in school when we have done a Boolean formulae. And this natural deduction or axioms are both sound and complete, A method is said to be sound if the result which it produces is correct. And a method is said to be complete if it will produce the correct result whenever possible. So this sort of natural deduction, as we shall see a little later, is both sound and complete. So natural deduction consists of the following set of rules. The first rule is called modus ponens. Modus ponens says if A implies B is given and A is given, then B is also true. Modus tollens says if A implies B is given and not B is given, then not A is true. It can easily be proved. We know that A implies B is true and we know that not B is true. If not B is true, then obviously if A was true, then B would have been true. Therefore, not A has to be true. Then it is the hypothetical syllogism which says if A implies B is true and B implies C is true, then A implies C is also true. This came from the old Greek and Indic thoughts where this is the transitive rule. Then there is the disjunctive syllogism which says if A or B is true and not A is true, then obviously B must be true. Because if A or B has to be true and not A given is true, then B must be true, otherwise A or B will not be false. Not be true. Similarly, we have the constructive dilemma, the destructive dilemma, the simplification. If A and B are true, therefore A is true. And we have the conjunction, if A is true and B is true, then A and B is true. We have addition, if A is true, then A or B is also true. And using the steps of natural deduction, we can prove whether any formula is true or not. And we can convert any formula to any other formula if the same exists. And this natural deduction is sound and complete, which means that if something can be proved in Boolean logic, it will be proved by, if something is proved by natural deduction in Boolean logic, then it is correctly proved. And complete means that if something can be proved, then it will be proved. So it has got both ways connection. However, propositional logic does not allow us to encode all types of reasoning. Here are 4 examples. Wherever Mary goes, so does the lamb. Mary goes to school, so the lamb goes to school. Now here the question is, what will we assign as Boolean variable? Because if we says Mary goes to school is one Boolean variable, but how will we encode wherever Mary goes? So this is where we are facing problem and in trying to encode in propositional logic. The second example, no contractors are dependable. How will we encode this? We can say contractors are dependable, contractors are not dependable. But there is no contractor who is dependable. Similarly, some engineers are contractors. So we are entering into a domain where we talk about everybody, somebody, everything, something, nobody. So this is not easily encodable in Boolean logic or propositional logic. All dancers are graceful. Ayesha is a student. This can be done in Boolean logic. Ayesha is a dancer. This also can be done in Boolean logic. But all dancers are graceful. Therefore, some student is graceful. These two parts cannot be done in propositional logic. Last example, every passenger is either in first class or second class. Each passenger is in second class if and only if he or she is not wealthy. Some passengers are wealthy. Not all passengers are wealthy. Therefore, some passengers are in the second class. As we see, while we can do a large set of problems and encode them in propositional logic, it is not sufficient for us for our deeper reasoning. And for this, we will move on to predicate logic, which will be the second in the series of these lectures, or higher order logic. With this, we come to the conclusion of our lecture on propositional logic. Thank you very much for your attention. In the subsequent lecture will be on propositional logic, how we move from propositional logic to predicate logic. Thank you very much.